Hello and welcome. Today, we're diving into the fascinating world of sequences and series. By the end of this video, you will be able to define a series, understand and use sigma notation, and apply the fundamental properties of sigma notation to solve problems. Our main topics will be the definition of a series, sigma notation, and the properties of sigma notation. These concepts are foundational in mathematics and appear in many areas, including calculus and statistics. Let's get started. First, let's clarify what a series is. You're likely familiar with sequences, which are ordered lists of numbers. A sequence is simply a list of numbers, like 2, 4, 6, 8, and so on. A series is closely related. It's the sum of the terms of a sequence. So if we take the terms of a sequence and add them together, we get a series. For our example, the series would be 2 plus 4 plus 6 plus 8, and so on. We can talk about two types of series, finite and infinite. A finite series has a specific, limited number of terms. For example, the sum of the first 5 terms of our sequence would be 2 plus 4 plus 6 plus 8 plus 10, which equals 30. This sum is always a finite, real number. An infinite series, on the other hand, has an infinite number of terms. It continues forever. In many cases, the sum of an infinite series cannot be calculated, but in some special cases, it can converge to a finite number. We'll explore this more in a future lesson. So to recap, a series is the sum of the terms of a sequence. It can be finite, with a sum that is always a real number, or infinite, which may or may not have a finite sum. Writing out long series can be tedious. Fortunately, mathematicians have developed a compact and powerful notation for sums, called sigma notation. This is sigma notation. The symbol is the Greek letter sigma, which is the equivalent of the capital S in our alphabet, standing for sum. Let's break down how it works. A typical sigma notation expression looks like this. Let's examine each part. V, U sub k, is the general term of the sequence. It's a formula that tells you how to find any term in the series. The general is called the index of summation. It's a variable that we substitute into the general term. The number below the sigma, k equals 1, is the lower limit. It tells us where to start our summation. In this case, we start with the first term. The number above the sigma, nin, is the upper limit. It tells us where to stop. We sum all terms from the lower limit up to the upper limit. So this expression reads, the sum of all numbers of the form u sub k, where k starts at 1 and goes up to n. This is equivalent to writing out the series u sub 1 plus u sub 2 all the way up to u sub n. It's a much more concise way to represent the sum. To summarize, sigma notation provides a compact way to write a series, specifying the general term, the index, and the starting and ending points of the summation. Let's put this into practice with an example. Our goal here is to expand and evaluate a series written in sigma notation. Consider the expression, the sum from k equals 1 to 7 of the term k plus 1. To expand this, we substitute each integer value of k from the lower limit, 1, to the upper limit, 7, into the general term k plus 1, and then add the results. When k is 1, the term is 1 plus 1, which is 2. When k is 2, the term is 2 plus 1, which is 3. We continue this process for k equals 3, 4, 5, 6, and 7. So, the expanded series is 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. Now, to evaluate it, we simply add these numbers together. The sum of these terms is 35. So, the value of the series is 35. Let's try another one. This time, the general term is a fraction. We need to expand and evaluate the sum from k equals 1 to 5 of 1 over 2 to the power of k. Again, we substitute k equals 1, 2, 3, 4, and 5 into the general term. For k equals 1, we get 1 over 2 to the 1, which is 1/2. For k equals 2, we get 1 over 2 squared, which is 1/4. We continue this for k equals 3, 4, and 5. The expanded series is 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. To evaluate this, we need to find a common denominator, which is 32. Converting each fraction to have a denominator of 32, we get 16 30-seconds plus 8 30-seconds plus 4 30-seconds plus 2 30-seconds plus 1 30-second. Adding the numerators, we get 31 over 32, so the sum of this series is 31 30-seconds. In summary, to expand and evaluate a series in sigma notation, you substitute each integer from the lower to the upper limit into the general term, and then add all the resulting terms. Now, let's look at some powerful properties of sigma notation that can simplify our calculations. Our goal is to understand and apply these properties. These properties are essential tools for manipulating and evaluating series. The first property is the sum of a constant. If you are summing a constant, c, from k equals 1 to n, the result is simply the constant multiplied by the number of terms, n. This is because you are adding c to itself n times. Let's see an example. Suppose we want to find the sum from k equals 1 to 5 of the constant 3. Using the property, we multiply the constant, 3, by the number of terms, 5. The result is 15. If we were to expand it, we would have 3 plus 3 plus 3 plus 3 plus 3, which also equals 15. The second property is the constant multiple rule. If your general term is a constant, c, multiplied by a function of k, you can pull the constant out in front of the summation. This means you can sum the function of k first, and then multiply the result by the constant. Here's an example. Let's evaluate the sum from k equals 1 to 3 of 4k. Using the property, we can pull the constant 4 out. Now we just need to sum k from 1 to 3, which is 1 plus 2 plus 3, giving us 6. Then we multiply by 4 to get 24. The third property is the sum and difference rule. If your general term is a sum or difference of two functions of k, you can split the summation into two separate summations. This allows you to evaluate each part independently and then add or subtract the results. Let's see this in action. We want to evaluate the sum from k equals 1 to 4 of 3 k minus 5. We can split this into two summations, the sum of 3k minus the sum of 5. Now we can apply the constant multiple rule to the first part and the sum of a constant rule to the second part. This gives us 3 times the sum of k minus 5 times 4. The sum of k from 1 to 4 is 1 plus 2 plus 3 plus 4, which is 10. So we have 3 times 10 minus 20, which equals 10. To recap, we've learned 3 key properties: the sum of a constant, the constant multiple rule, and the sum and difference rule. These properties allow us to break down complex summations into simpler, more manageable parts. Let's work through a more complex example that combines these properties. Our goal is to evaluate a series with a quadratic general term. We need to evaluate the sum from k equals 1 to 5 of k times the quantity k plus 1 times the quantity k plus 2. The first step is to expand the general term. This will allow us to use the sum and difference rule. Multiplying k plus 1 by k plus 2 gives us k squared plus 3k plus 2. Then, multiplying by k, we get k cubed plus 3k squared plus 2k. Now we can rewrite our original summation with this expanded general term. Next, we apply the sum and difference rule to split this into 3 separate summations. This gives us the sum of k cubed plus the sum of 3k squared plus the sum of 2k. Now, we apply the constant multiple rule to the second and third summations. We pull the 3 out of the second sum and the 2 out of the third sum. This leaves us with 3 standard summations. Now we just need to evaluate each of these 3 parts. Let's start with the sum of k. The sum of k from 1 to 5 is 1 plus 2 plus 3 plus 4 plus 5, which equals 15. Next, the sum of k squared. The sum of k squared from 1 to 5 is 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, which is 1 plus 4 plus 9 plus 16 plus 25, totaling 55. Finally, the sum of k cubed. The sum of k cubed from 1 to 5 is 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed, which is 1 plus 8 plus 27 plus 64 plus 125, totaling 225. Now we substitute these values back into our expression. We have 225 plus 3 times 55 plus 2 times 15. This simplifies to 225 plus 165 plus 30, which gives us a final answer of 420. So by expanding the general term and applying the properties of sigma notation, we were able to evaluate this complex series. This process is a powerful tool for solving many problems in series. Let's tackle another type of problem, writing a series in sigma notation. Our goal is to take an expanded series and express it compactly. Consider the series 3 plus 11 plus 19 plus 27 and so on up to the 10th term. The first step is to identify the type of sequence. Let's look at the differences between consecutive terms. The difference between 11 and 3 is 8. The difference between 19 and 11 is 8. And the difference between 27 and 19 is also 8. Since the difference is constant, this is an arithmetic sequence. For an arithmetic sequence, the general term, u sub k, is given by the formula u sub 1 plus k minus 1 times d, where u sub 1 is the first term, and d is the common difference. In our series, the first term, u sub 1, is 3, and the common difference, d, is 8. Now we substitute these values into the formula for the general term. This gives us u sub k equals 3 plus the quantity k minus 1 times 8. Let's simplify this expression. Distributing the 8, we get 3 plus 8k minus 8, which simplifies to 8k minus 5. This is our general term. Now we have all the pieces for our sigma notation. The general term is 8k minus 5. The lower limit is k equals 1, since we start with the first term. And the upper limit is 10, since we are summing 10 terms. Putting it all together, the series can be written as the sum from k equals 1 to 10 of 8k minus 5. Let's try another one, this time with a geometric sequence. Consider the series 12 plus 6 plus 3 plus 1.5, and so on, up to the 8th term. To identify the type of sequence, we look at the ratio between consecutive terms. 6 divided by 12 is 0.5. 3 divided by 6 is 0.5. And 1.5 divided by 3 is 0.5. Since the ratio is constant, this is a geometric sequence. For a geometric sequence, the general term, u sub k, is given by the formula u sub 1 times r to the power of k minus 1, where u sub 1 is the first term and r is the common ratio. In our series, the first term, u sub 1, is 12, and the common ratio, r, is 0.5. Now we substitute these values into the formula for the general term. This gives us u sub k equals 12 times 0.5 to the power of k minus 1. This is our general term. Finally, we assemble our sigma notation. The general term is 12 times 0.5 to the k minus 1. The lower limit is k equals 1, and the upper limit is 8. So the series can be written as the sum from k equals 1 to 8 of 12 times 0.5 to the power of k minus 1. To summarize, to write a series in sigma notation, first identify the type of sequence to find the general term, then determine the lower and upper limits of the summation. Sometimes, the lower limit of a summation is not 1. Our goal in this scene is to learn how to evaluate series that start at an index other than 1. Consider the expression. The sum from k equals 6 to 12 of 100 times 1.2 to the power of k minus 3. There are two main ways to approach this. The first is to simply expand the series. We substitute k equals 6, 7, 8, and so on, up to 12, into the general term. This gives us a series of 7 terms. The expanded series is 100 times 1.2 cubed, plus 100 times 1.2 to the 4th, and so on, up to 100 times 1.2 to the 9th. This is a geometric series. We can use the formula for the sum of a finite geometric series, S sub n equals u sub 1, times the quantity r to the n minus 1, all over r minus 1. In this series, the first term, u sub 1, is 100 times 1.2 cubed. The common ratio r is 1.2, and the number of terms, n, is 12 minus 6 plus 1, which is 7. Plugging these values into the formula, we get 172.8 times the quantity 1.2 to the 7th minus 1, all over 1.2 minus 1. Calculating this gives us approximately 1000.4. A second method is to use a change of index. We can rewrite the summation so that the lower limit is 1. Let's define a new index, j, as k minus 5. This means that when k is 6, j is 1. When k is 12, j is 7. And k is equal to j plus 5. Now we substitute j into our original expression. The summation becomes the sum from j equals 1 to 7 of 100 times 1.2 to the power of j plus 5 minus 3. This simplifies to the sum from j equals 1 to 7 of 100 times 1.2 to the power of j plus 2. This is the same geometric series we found with the first method, just written with a different index. Both methods lead to the same result. In summary, to evaluate a series with a lower limit other than 1, you can either expand it and use the appropriate series formula, or you can perform a change of index to rewrite it with a lower limit of 1. Let's explore a classic problem that demonstrates the power of sigma notation and algebraic manipulation. Our goal is to derive a formula for the sum of the first n integers. We want to find a simple expression for the sum from k equals 1 to n of k. Let's call this sum s sub n. So s sub n is equal to 1 plus 2 plus 3 all the way up to n. Now, here's the clever part. Let's write the same sum in reverse order. S sub n is also equal to n plus n minus 1 plus n minus 2 all the way down to 1. Now let's add these two equations together, term by term. On the left side, we have s sub n plus s sub n, which is 2 times s sub n. On the right side, notice what happens when we add the corresponding terms. The first pair is 1 plus n. The second pair is 2 plus n minus 1, which is also n plus 1. The third pair is 3 plus n minus 2, which is also n plus 1. Every single pair adds up to n plus 1. How many of these pairs are there? There are n terms in the original series, so there are n pairs. This means we are adding n plus 1 to itself n times. So 2 times s sub n is equal to n times the quantity n plus 1. Finally, to solve for s sub n, we divide both sides by 2. This gives us the famous formula for the sum of the first n integers. S sub n equals n times n plus 1, all divided by 2. This formula is incredibly useful. For example, the sum of the first 100 integers is 100 times 101 divided by 2, which is 5050. Much faster than adding them all up. To recap, by writing the sum in both forward and reverse order and adding them, we were able to derive a simple and elegant formula for the sum of the first n integers. Let's use the formula we just derived to solve a more advanced problem. Our goal is to find the values of constants, a and b, in a given summation. We are given that the sum from k equals 1 to n of the term ak plus b is equal to 8n squared plus 11n for all positive integers n. We need to find the values of a and b. We can solve this by using the properties of sigma notation and comparing the resulting expression with the given one. First, let's expand the left side of the equation using the sum and difference rule. Next, we apply the constant multiple rule to the first term and a sum of a constant rule to the second term. This gives us a times the sum of k plus b times n. Now, we substitute the formula we just derived for the sum of k. The sum of k is n times n plus 1, all over 2. So our expression becomes a times n plus 1 over 2, plus b, n. Let's simplify this expression by expanding and collecting terms. We get a times n squared plus n over 2 plus bn. This can be written as a over 2 times n squared plus a over 2 times n plus bn. Now, let's group the terms with n. This gives us a over 2 times n squared plus the quantity a over 2 plus b, all times n. We are given that this expression is equal to 8n squared plus 11n. For these two polynomials in n to be equal for all values of n, their corresponding coefficients must be equal. This is a powerful technique called comparing coefficients. First, let's compare the coefficients of n squared. The coefficient of n squared on the left is a over 2, and on the right is 8. Setting them equal, we get a over 2 equals 8, which means a must be 16. Now let's compare the coefficients of n. The coefficient of n on the left is a over 2 plus b, and on the right is 11. Setting them equal, we get a over 2 plus b equals 11. We already found that a is 16. Let's substitute that in. 16 over 2 plus b equals 11. This simplifies to 8 plus b equals 11, which means b must be 3. So we have found our constants. A equals 16 and b equals 3. To recap, we used the properties of sigma notation to expand the left side of the equation, then compared the coefficients of the resulting polynomial in n with the polynomial on the right side to solve for the unknown constants. Let's conclude with a final, more challenging problem that brings together several concepts. Our goal is to find a simplified expression for a summation involving a product. We need to find a simplified expression for the sum from k equals 1 to n of the quantity k plus 1 times the quantity k plus 2. The first step, as before, is to expand the general term. Multiplying k plus 1 by k plus 2 gives us k squared plus 3 k plus 2. So our summation becomes the sum from k equals 1 to n of k squared plus 3k plus 2. Now, we apply the sum and difference rule to split this into three separate summations. This gives us the sum of k squared plus the sum of 3k plus the sum of 2. Next, we apply the constant multiple rule to the second term and the sum of a constant rule to the third term. This becomes the sum of k squared plus 3 times the sum of k plus 2n. At this point, we need two standard formulas. We already know the formula for the sum of k. We also need the formula for the sum of k squared. The sum of k squared from 1 to n is n times n plus 1 times 2n plus 1, all divided by 6. Now we substitute these two formulas into our expression. This gives us n times n plus 1 times 2n plus 1 over 6, plus 3 times n plus 1 over 2, plus 2n. Our goal is to simplify this. The best way to do this is to find a common denominator, which is 6, and factor out any common terms. Let's rewrite each term with a denominator of 6. The first term is already there. The second term becomes 9n times n plus 1 over 6. The third term becomes 12n over 6. Now we can combine the numerators. We can also factor out a common term of n over 6. Let's simplify the expression inside the brackets. Expanding the terms, we get 2n squared plus 3n plus 1 plus 9n plus 9 plus 12. Combining like terms, this simplifies to 2n squared plus 12n plus 22. We can factor a 2 out of the quadratic inside the brackets. This gives us n over 6 times 2 times the quantity n squared plus 6n plus 11. Finally, we can simplify the fraction 2 over 6 to 1 over 3. Our simplified expression is n over 3 times the quantity n squared plus 6n plus 11. To recap, we expanded the general term, used the properties of sigma notation to split the sum, applied standard formulas for the sums of k and k squared, and then used algebraic manipulation to simplify the result. Let's quickly recap what we've learned today. We started by defining a series as the sum of the terms of a sequence. We then introduced sigma notation as a compact way to write a series, with a general term, an index, and upper and lower limits. We explored the key properties of sigma notation, the sum of a constant, the constant multiple rule, and the sum and difference rule. These properties are crucial for manipulating and evaluating series. We also saw how to derive the formula for the sum of the first n integers, and how to apply these concepts to solve more complex problems, including finding unknown constants and simplifying expressions. You are now equipped to define a series, use sigma notation, and apply its properties. Keep practicing these skills, as they are fundamental to many areas of mathematics. To solidify your understanding, here are 5 practice questions. Take your time to work through them, and remember to use the properties and techniques we've discussed. Here are the questions. Pause the video now to give yourself time to solve them. Welcome back. Let's go through the answers. For question 1, the sum is 40. For question 2, the series is the sum from k equals 1 to 12 of 4k plus 1. For question 3, the sum is 145. For question 4, c equals 12. And for question 5, the simplified expression is n over 3 times n squared plus 9n plus 26. I hope you found this video helpful. Thank you for watching.